Hello, my name is Felix Freitag. I will present our paper called REDEMON, Resilient Decentralized Monitoring System for Edge Infrastructures. We are researchers from the Technical University of Catalonia in Barcelona, Spain, and from Southeast European University in North Macedonia. The structure of this presentation is: first I will explain the objectives, then the legacy monitoring system that we have today. Then we go to the REDEMON design and implementation and its evaluation, and finally the conclusions. The objective is to build a monitoring system for the GIFI community network. You see this photo on the right side of the slide, the nodes and links of GIFInet in the area of Barcelona. And these nodes, or these green points, actually represent wireless routers, which you can see on the left side. And these are the network devices which we want to monitor. Basically, we want to do ping and SMP operations to know about the network. And we want to do this with using distributed edge devices to host the monitoring system, like the ones that you can see on the bottom at the right side. So GIFInet today has already a monitoring system, which we call the legacy monitoring system. And this slide explains how it works. Basically, we have a set of monitoring servers, which are these gray boxes, and they have assigned a list of network devices, the routers, like this. They are assigned statically with the help of a MySQL database, which contains the list of monitoring servers and the list of nodes to be monitored. And each node is monitored at most by one monitoring server. What is the problem? Well, we have a lack of robustness, resilience, and adaptability in the current system. For instance, if any link breaks, like here, then this node will not be monitored anymore. Or if any monitor shuts down, this also means that this node will not be monitored anymore. So we want to build a new monitoring system which should have automatic assignment. So we want that there's not static assignment anymore, but monitors automatically assigned to network devices. We want to have automatic work configuration. So when there are changes in the network, the system will adapt to these changes. Redundancy, well, if any node or monitor fails, there will be other monitors which are keep monitoring this node. Load balancing, we want to distribute the monitoring workload over the monitoring servers. And data replication, the monitored data should be replicated in the database. And we want that all these these new features will work on a monitoring system which runs on edge devices. So we have built the REDEMON system with 4 components, which we called fetch, assign, ping, and SMMP. They were implemented in Go, and we used also the Antidote DB database, which uses CRDT data types. We have 2 types of monitoring servers. There are the full-blown monitoring servers, which have 4 components plus the Antidote DB database instance. And we have the lightweight monitoring servers, which run these 4 components, but they use a remote Antidote DB instance. You can find the code of our components in public repositories. Now I will go into more details of the design. First, we use this Antidote DB database, which applies conflict-free replicated data types, or in short, CRDTs. So this database stores the mapping of this data structure that you can see in the middle, which can be seen as a table to host the mapping between nodes and monitoring servers which are assigned to these nodes. There are many instances of Antidote DB typically hosted along the monitoring servers. When the monitoring system starts, there is the monitor fetch operation, which uploads the nodes to the Antidote DB database. When the monitoring servers start, they run the monitor assign operation, so they will read the list of nodes and list of monitors from Antidote DB. They will check if there is any node which is not sufficiently monitored, and if they have capacities, they will auto-assign themselves to this node. And if any node has too many monitors, they will unassign themselves from this node. This should assure that every node at all time has the minimum number of monitoring servers. Once this list is updated, the monitoring servers do the ping operation to the nodes which are assigned to them, and they write the RTT data to the Antidote DB database, and they also perform the SNMP operation, the request, and they write this data also to Antidote DB. We have deployed a testbed to evaluate this monitoring system. We have done some tests in the lab, but the tests, the evaluation that I will show in the following, were done in these real nodes, Minix devices and Raspberry Pis, which were deployed in Gifinet. So the testbed that we used consisted of 10 Raspberry Pis and 8 Minix devices. The Raspberry Pis hosted lightweight monitoring servers, and the Minix device hosted the Antidote DB instances. First, we wanted to see if the assign operation works correctly, and for this we ran an experiment of duration of 10 minutes, we had a network of 54 devices to be monitored, and during these 10 minutes we started up to 10 monitors during the first 6 minutes, and then gradually we switched them off. So we could see that by around the second 340, all the devices, 54 networking devices, had assigned a minimum of 4 monitors, which was correct. And when the monitors switched off gradually, the devices became unassigned, which was expected. We also looked if the number of assigned devices was correct. So in the experiment of 10 minutes, when we at time 340 seconds we had the 10 monitors running, we got 216 devices assigned, which corresponds to 4 monitors for each of the 54 devices. So this was also correct. Then we looked at the CPU and memory consumption of our solution. This is important because we use mini PCs, low capacity devices, to run the monitoring system. So first we look at the fetch operation, and we see in the red curve that during the fetch operation less than 1 core is used, and also out of the 4 gigabytes which are on the Minix device, only around 165 megabytes were used. So this operation was not a problem with the resource consumption. We also looked at the bandwidth. So we found that during the fetch operation, a traffic of around 700 to 800 kilobits per second was produced. We saw that also outgoing traffic was produced, not only incoming. So the reason for this is that antidote DB databases synchronize with each other their content. Then we looked at the resource consumption for the assigned ping and SMP operation, which corresponded to the normal operation of the monitoring system, and we found that CPU is around 1 core of the 4 cores, and net memory consumption was between 400 to 500 megabytes of the 4 gigabytes available. So there was it's moderate resource consumption for the devices that we have available. We also looked at the traffic in the assigned ping and SMP operation, and here we saw that traffic is between 1000 and 2000 kilobits per second. This principle for most links in the wireless network, this is acceptable, and because they have a much higher bandwidth. But there could be some low capacity links in Gifinet for which this traffic is high. So it's something that has to be checked, where the monitoring monitoring servers are placed. They should not be placed at too low capacity links. Then we come to the comparison of the REDEMON monitoring system with the legacy monitoring system. We have achieved an automatic assignment because we saw that the monitors are able to self-assign itself to the devices. They are also able to reconfigure automatically if there are any changes in the system. There is a redundancy in the new monitoring system since every network device has several monitors. We can do load balancing between the monitoring servers, and there is data replication of the monitoring data. It is replicated with full replication in the Antinode DB database. As a conclusion, we have seen the design of a distributed monitoring system for dynamic networks in which the network devices and the monitoring servers can join and leave certain frequency. We have done a functional evaluation and also the evaluation of the resource consumption of our solution, and we have achieved robustness, resilience, and adaptability by the help of this decentralized coordination which the monitoring servers do over the Antinode DB database. If you have any questions about our paper, please contact me at my email. Thank you.